Hello! So today we're going to be doing exponential applications. So exponential applications, they come with a formula, and I'm going to tell you what each one means, aka this, what each variable stands for in the formula, and then we're going to discuss about why we need to know that and how that's going to help us. And then we're going to solve some exponential application questions. We're going to start off easy, and then we're going to get to harder questions as we go along. So thank you very much for watching, and let's begin. So we have the formula right here. A equals A naught, brackets 1 plus minus R, bracket again, T over N, and that's an exponent. So A is final amount, A naught is starting or initial amount, R is growth or decay rate, T is time elapsed, and N is growth or decay time. So I'm going to give you a moment to write that down. It's sort of a legend, and we're also going to be doing the same legend but with actual numbers later on when we solve our exponential application questions. T and N must be the same units. So if you're going to solve for T, or if you're going to solve for T, then it's going to be in the same units that you input N. So what does each variable mean within the formula, and how is that going to help us? Well, if we know what each one stands for or means, we'll have a much better understanding of how to solve for exponential applications. So I'll give you a moment to write this down. So final amount is the final amount. We often solve for A or we solve for T in these equations. So A or T is what we're solving for. And then sometimes we solve for R. Okay, so A is final amount, A naught or A0, that little zero there stands for A naught, is starting or initial amount, R is growth or decay rate, T is time elapsed, and N is growth or decay time. So I'm having trouble trying to explain what each one means, but maybe as we start these exponential applications, you'll follow along and then understand what each of them mean. So, let's begin. A radioactive material has a half-life of 12 hours. We have two questions here. Most of them are two-parters. If you start with 100 grams, how much is left in half an hour? And question 2 is how long until 20 grams is left? Okay, so the first question is, if you start with 100 grams, how much is left in half an hour? So we're starting with 100 grams, so initial amount is 100 grams. We don't know what the final amount is. 1 plus minus R is just going to be half, because it's a half-life. Half-life or doubling period is, so we use terms like half-life, we use terms like doubling period. Half-life is just half, and then doubling period is 2. And then T, time elapsed, how much is left in half an hour, so half an hour. And radioactive material has a half-life of 12 hours, so our decay time is 12 hours. Actually, I'm going to go back here. I'm going to do 0.5 hours, 12 hours. So here we have everything, we have our legend here. Does everyone understand does everyone understand this? So A is final amount, A naught is initial amount, A plus minus R, that's decay rate, T is time elapsed, and N is growth or decay time. So A naught, we start with our initial amount is 100 grams. We have a half-life. Half-life means half. So our growth or decay time is half. Our growth or decay rate is half. We have time elapsed, and it's how much time has gone past is half an hour. And then we have growth or decay time, which specifies in the question that it's 12 hours. So I'm hoping you understand that. And then we're gonna use the formula. I always like to write the formula to begin with, and then we can start plugging in numbers. So it's 0.0416666667. So if we plug the line that was just written into our calculator, we should get 97.1531949 grams. So that's how much is left after half an hour. We're gonna circle our answer. So me personally, when I'm doing exponential applications, I like the full answer written, and then when I'm doing the therefore statement, I'll only go to 4 decimal places. It's best for accuracy. I always input the units, so what units we're doing. Okay, so after half an hour, there will be 97.1532 grams left of the radioactive material. So, we solved question number 1. If you start with 100 grams, how much is left in half an hour? And then question 2 says, how long until 20 grams is left? How long until 20 grams is left? So, our final amount is 20 grams. We started with 100 grams. We have a half-life, so our decay rate is half. Time elapsed, we don't know. And our has a half-life of 12 hours, so our decay time is 12 hours. So the time that we get is going to be in the same units as N, and N is in hours. So now we're solving for T. Remember, we usually solve for A or T. So we're going to log both sides. And then we're going to use the power log of laws. So it's going to bring this exponent down to here. So to get rid of that 12 on the bottom, I'm going, because it's t divided by 12, I'm just going to multiply both sides by 12. So we're going to circle our answer and we're going to add our units. Our units is hours because for n we put in 12 hours and it has to be the same units. T and n are always the same units. So it's 27 hours, 0.86313714 hours. But when we do our therefore statement, we're going to go to 4 decimal places, just for accuracy. So it will take 27.8631 hours until 20 grams is left of the radioactive material. So I'll give you a minute to write all of that down. And would you like to go over this again, just to make sure people understand? So we have A, which is our final amount. It says how long until 20 grams is left. And our final amount is 20 grams. A naught, and it was our initial amount was 100 grams, and that was specified in question 1. If we start with 100 grams, how much is left in half an hour? So that was question 1. So our initial amount would be 100 grams. We have our half-life, so 1 plus minus r, aka our rate of growth or decay, would be a half. We have the time elapsed. We don't know the time. Well, now we do. It's 27 hours followed by some decimals. We solved for t, and our t was time elapsed. How long until we have 20 grams left? And then our growth and decay time was 12 hours. It was specified in the question that it had a half-life of 12 hours. So that's what our legend means. Hopefully you had time to write all that down, and we're going to move on. A certain bacteria doubles every 20 minutes. Suppose that there are 200 bacteria to start. So we have doubles. Doubling period is every 20 minutes. So 1 plus minus r is going to be 2. We have it doubles every 20 minutes. So we have n. N would be 20 minutes. And suppose that there are 200 bacteria to start with. So A naught, or that A with that little circle, is going to be 200. How many bacteria is there after 3 hours? And that's question 1. And question 2 is, how long will it take to reach 1 million bacteria? That sounds like a large number. Okay, so let's start with question 1. So, how many bacteria is there after 3 hours? Our time elapsed is 3 hours. Our growth or decay time is 20 minutes, and those are different units. So I'm gonna do 180 minutes because it's 3 hours, 60 minutes in an hour. 60 times 3 is 180 minutes. We have 1 plus and minus r, and it's doubles. So 1 plus minus r is going to be 2. It says, suppose that there are 200 bacteria to start with. So we're going to do 200 bacteria for our A naught. And then we don't know how many bacteria is there after 3 hours. So we don't know how many bacteria there is after 3 hours, so we're solving for final amount. So I like to write the formula first, and let's get started. So if we plug our final line into our calculator, we should get 102,400 bacteria. So that's how many left after 3 hours. Let's do our therefore statement. So I'm just going to rewrite the word bacteria. Okay, there will be 102,400 bacteria after 3 hours, or 180 minutes. I put both just to be clear. Remember that T and N have to be the same units, so we converted 3 hours into minutes. So we have the same units for T and N. So our second question is, how long will it take to reach 1 million bacteria? So we have our final amount, that's 1 million bacteria, and we want to know how long it takes. So we're solving for T, the time elapsed. 1 million. We're looking for 1 million bacteria. We started with 200 bacteria. It doubles. We don't know the time elapsed. And it's 20 minutes for our doubling period, or our growth time. And just so you know, since we're solving for t, since n is in the units of minutes, t will also be minutes. We're gonna log both sides so we can get the exponent to come down. Since t is divided by 20, I'm multiplying on both sides to get rid of the division. Since t is divided by 20, I'm multiplying both sides by 20 so I can isolate t and get t by itself. If you plug the last line that we just wrote into your calculator, you should get 245.7542476 minutes. Let's circle our answer. Sorry, just circling the therefore statement. So, it would take 245 minutes, 0.7542476 minutes, to reach 1 million bacteria. So now it's time for therefore statement. Sorry. So 7542. The 6 would make 7 become 8, 8 would become 5, 5 is the middle point, so I'm going to do 3. Since we're rounding up, it would take 245.7543 minutes to reach 1 million bacteria. So, that was question 2. Question 1 and 2 were easy, but after that it gets a bit more challenging, so keep that in mind. Determine the depreciation rate for a truck that was sold for $125,000 and the value after 3 years is $85,000. So 3 years have passed and it depreciates yearly. So our depreciation rate time is going to be 1 year. The time passed has been 3 years. We don't know the depreciation rate, so we're going to solve for R and we're going to isolate R. Our initial amount was $125,000, and then $85,000 is our final amount. So that's the amount of the car after 3 years. So let's do our formula. So, is that right? Yeah, that's right. So because we have the exponent of 3, we're going to do exponent of 1 over 3 on each side. So it's going to get rid of that exponent on the right side, and we're going to add the exponent of 1 divided by 3 to 0.68 on the left side. So we are left we're gonna do 1 minus R because it's a depreciation rate. So we're gonna go with 1 minus R. So I moved this 1 to the other side. It was a positive 1, so we're going to switch the operational sign. So it's going to be 0.68 to the power of 1/3 minus 1. And we have negative R on this side because it's a depreciation rate. We went with the negative, and the negative's still there, but we're going to factor that out, or we're going to cancel it out, or we're going to divide it out. So if we plug this into our calculator, we get negative 0.120634066, negative R. We want R by itself, so we're going to factor out a negative 1. So R is 0.120634066. 34066. We're gonna, in our therefore statement, we'll go to the 4th decimal place, and then in our percentage, we're gonna go to the 2nd decimal place. I know that we normally do units, but this is a question in which we solve for R, and R is usually a percentage, and we can, decimals and percentages are very similar, so we just left it as a decimal, and then we did the percentage in the therefore statement. So, we solved for R. That's the first time we solved for R. If you need any help, with questions that solve for R in particular, I suggest finding a textbook and doing questions that model this type of question. But we're gonna move on to question number 2, and question number 2 is, when will the value of the truck reach $3,000? So we're solving for T. Okay, so we have A equals A naught 1 plus minus RT over N. So, I had trouble with spacing, but the exponent should be after the bracket, and it's T over 1, just in case anyone was having issues seeing that. We're going to log both sides. So our answer is 29.02143092, and that's years. Because n was in years, so our t will be in years. Again, we go to the fourth decimal place in our therefore statement, and we write out the entire answer in our equation, or the last line of the equation, and it's just for accuracy. Okay, I'll give you a second to write all that down. Just a reminder, our question was, question 2, when will the value of the truck reach $3,000? I'm just gonna double check our calculation here. 3,000 divided by 125,000. And our answer is 0.024. It's only to the third decimal place, but that's the answer. Normally I would prefer to the fourth decimal place, but this is all it gave us, so don't worry about it. Moving on. So, a population of 1,500 algae doubles every 8 hours. How long will it take for the population to reach 25,000 algae? So, our initial amount is 1,500 or 1,500, 1,500, however you want to say it. 1 plus minus r is 2 because it doubles. The time elapsed we're solving for, and our growth time is every 8 hours. And how long will it take for the population to reach 25,000? So, this is just a question. It's just one question. Usually they're in 2 parts. Okay, let's start. So for our 25,000 divided by 1,500 is 16 0.666666667. There are seven sixes, and then 1 7. We are going to log both sides. So it's, since t is divided by 8 and we're trying to isolate t, we're going to multiply both sides by 8. So t is 32.47114951, and it's in years. Oh no, I'm wrong. It's in hours. Since n is in hours, t will also be in hours. So again, when we do our therefore statement, we're going to do the 4 decimal places. Since that 9 is going to make this a 5, we're going to bump 1 up to 2 because we're rounding up. So it's going to take 32.4712 hours for the algae to reach 25,000. There you go. So I'll give you a moment to write that down. That was question 4. We have one more question, and then we're off to trigonomic functions. One more question, and then we'll be done. So Malcolm bought a computer system for $4,000. The system depreciates at a rate of 18% each year. Determine the value of Malcolm's computer system 5 years from now. And question 2 is, when will the computer be worth less than $500? So we know that the computer system was bought initially for $4,000, so our initial amount, or A0, is going to be $4,000. We know that the system depreciates at a rate of 18% per year. It depreciates at a rate of 18% each year, so it's going to be 1 minus 0.18. And I think it's 0.82. And it depreciates yearly, so our depreciation time, or our decay time, is going to be 1 year. So let's get started. I was just letting you know what the information in the information part of the question, what it means. So $4,000, we're solving for A, for question 1, determine the value of Malcolm's computer system 5 years from now. So we're determining the final amount, and it's 1 minus 0.18, which equals 0.82, and it's 5 years from now, and our depreciation or decay rate time is going to be 1 year. So t is 5 and n is 1. So if we plug this into our calculator, we should get 1,482.959373. Because it is money, we're going to go to the second decimal place because it's money. Let's do our therefore statement. Because the third decimal place is a 9, we're going to round up to 6. So we're going to the second decimal place because it is money, and money goes to the second decimal place. It doesn't go for longer than the second decimal place. It's just like we go to the nearest cent, and the nearest cent is the second decimal place. So it's going to be 5 years from now, the value of the computer system will be $1,482.96. And that's written there. So I'll give you a minute to write that down. So, question 2. When will the computer be worth less than $500? So, our final amount is $500. Actually, our initial amount is $4,000. It depreciates at 18% per year, so it's 1 minus 0.18, which is 0.82. We don't know the time because it says how much, because our question is when will the computer be worth less than $500? So we're solving for when, so we're solving for the time elapsed until the computer is worth less than $500. And it depreciates yearly, which means that our decay time is going to be 1 year. So, 0.125. Normally I would go to the fourth decimal place, but the answer gives us only to the third decimal place. So 0.125 is 500 divided by 4,000. And we got rid of the 4,000 on this side, so we're just left with 0.82 t. Since t is over 1, I'm going to get rid of the 1 and just say it's t, because anything over 1 is just the numerator itself. So let's begin. Let's log both sides. So our answer, since n is in years, t will also be in years, so our answer is 10.4783656. So 10.4783656, and that's years. Let's circle our answer, and let's write our therefore statement. We're going to the 4th decimal place. And because the 5th decimal place is a 6, it's going to turn that 3 into a 4. So it will take 10.4784 years until the computer system is worth less than $500. There you go, we circled all of our answers. Okay. So we're going to move on to trigonomic functions in the next few videos. This is the last of exponential functions, or exponential functions. Yeah, I got it right. This is the last of exponentials, and we're going to be moving on to trigonomic functions, and that's going to take quite a few videos. And then we'll be moving on to composite functions and rates of change. I've already done a video on rates of change, so we might just do composite functions. But composite functions is a really small and easy unit, so you'll get it right away. And I will try my best to do trigonomic functions. And so I hope you found this video helpful in any way to solving for a, t, and even r. I'll show you. We solve for a, t, and 1 plus minus r. So those are the variables that we usually solve for when we're doing exponential applications. And thank you very much for watching. I hope you found this helpful. If you have any questions, feel free to leave a comment, and I will be back with more math videos later this week. Thank you.